Black holes. Let's be honest, we think of them as the universe's ultimate monsters, right? The darkest villains in the cosmic story. But what if almost everything you think you know about them is just scratching the surface of a reality that's so much deeper, stranger, and frankly, more amazing? So let's just dive right in and start peeling back the layers on one of the greatest mysteries in all of science. Okay, so the very first thing we need to do is just toss out that pop culture image of a cosmic vacuum cleaner, the one that's just sucking up everything in its path. A black hole isn't a hole. It's not some patch of empty space. The truth is way more elegant and a lot more mind-bending. You see, according to Albert Einstein, mass tells space-time how to curve, and that curvature tells mass how to move. The classic analogy is a bowling ball on a trampoline. Well, a black hole is what you get when you have so much mass in such a tiny, tiny space that the trampoline doesn't just dip, it curves down infinitely. It creates this well in space-time so deep that all paths, even a path taken by a beam of light, can only lead inward. So to really get our heads around this, we've got to dissect one. We're going to break down the key parts that define this literal edge of reality. And we'll start with the one thing that makes a black hole in the first place. Here's the wild part. Every single object that has mass, from you to a planet to a star, has something called a Schwarzschild radius. Think of it as a critical threshold. If you could somehow squeeze all of an object's mass inside this specific radius, its gravity would become so ridiculously intense that the escape velocity, the speed you'd need to break free, becomes faster than the speed of light. And, well, since nothing can travel faster than light, a black hole is born. And this is where the idea becomes really tangible and just insane. To turn our sun into a black hole, you'd have to crush its entire mass down into a sphere just 3 kilometers across, basically the size of a small town. And what about the Earth? You'd have to compress our entire planet into something smaller than a marble, just 9 millimeters wide. That is the kind of density we are talking about. It's just staggering. Now, this Schwarzschild radius, this boundary, marks the edge of the black hole. We call it the event horizon. But it is so important to understand this is not a physical surface. You couldn't touch it or stand on it. It's a boundary of information. It's a point in space-time, and once you cross it, nothing you do can ever affect the outside universe again. It is quite literally a one-way door. And this is where reality just completely splits. Imagine you're watching a friend's spaceship fall into one. From your safe distance, you'd see it get slower and slower, its lights stretching out, getting redder and redder, until it looks like it's just frozen in time at the edge, fading away. But for the astronaut inside, they wouldn't feel a thing. They just sail right on through the boundary. The only difference is, now, every possible future path they could take leads to only one inevitable destination. And that one place is the center. According to Einstein's math, every bit of mass that falls into a black hole gets crushed down to a point with zero volume and infinite density. This is the gravitational singularity. It's a place where the fabric of space-time becomes infinitely curved. But hold on a second. Does a place like that, a point of actual, literal infinity, really exist in nature? Or is the very idea of a singularity a giant warning sign from the universe, telling us that our theories, our physics, are broken? Well, most physicists today think it's the latter. The singularity isn't a real destination. It's a signpost. It's pointing to the spot where general relativity, our brilliant theory of gravity and the very large, just falls apart. It's telling us that we need a deeper theory, one that can unite gravity with the bizarre rules of the very small, a theory of quantum gravity. Okay, so that is the mind-bending theory. But black holes aren't just sitting around in textbooks. In the real universe, they are some of the most powerful, most violent engines in the entire cosmos. They are actively shaping everything around them. You see, an active black hole is surrounded by this swirling inferno called an accretion disk. It's a chaotic disk of gas and dust and the shredded remains of stars, all spiraling inward and getting heated by friction to millions of degrees. This disk can glow brighter than an entire galaxy of stars. And sometimes this process launches these colossal jets of plasma from the black hole's poles, blasting out at nearly the speed of light for thousands of light years. These are the engines that power quasars, the most luminous objects we know of. And these cosmic engines are pretty much everywhere. We now know that at the heart of almost every big galaxy, including our very own Milky Way, there's a supermassive black hole lurking. Ours is called Sagittarius A star. It weighs as much as 4 million suns, and it's the immense gravitational anchor that our entire galaxy spins around. So, they are massive, they are powerful, and they're defined by a point of no return. For decades, that was the story. Whatever goes in never comes out. But then, a ghost entered the machine. Quantum mechanics showed up, and the entire story changed forever. Back in 1974, Stephen Hawking made a discovery that just completely shook physics. By applying the strange, fuzzy rules of quantum mechanics right at the edge of a black hole, where pairs of virtual particles are constantly popping into and out of existence, he realized something incredible. Black holes can't be perfectly black. They have to leak. They should faintly glow, emitting this tiny trickle of particles we now call Hawking radiation. And what that means is that black holes are not eternal prisons. They slowly lose mass. They evaporate. Now, don't worry, the universe isn't about to fizzle out anytime soon. For a typical black hole, one with the mass of our sun, the time it would take to completely evaporate is 10 to the power of 67 years. I mean, that number is so big, the entire age of the universe so far is a rounding error next to it. But it's the principle that matters. They are not forever. And this evaporation idea leads to one of the deepest, most profound problems in physics today. See, a fundamental rule of quantum mechanics is that information can never, ever be truly destroyed. But what if you throw a book into a black hole? The black hole eventually evaporates away into a featureless, random glow of radiation. So where did the information that made up the book go? This is the information paradox. It's a head-on collision between our two best theories of reality. And this right here, this conflict, brings us to the real reason why physicists are so utterly obsessed with black holes. They're not just weird objects out in space. They are the ultimate laboratory for testing our most fundamental ideas about the universe itself. So here's the key takeaway. Black holes force our best theories to confront each other. They are the arena where the smooth, predictable, curved world of Einstein's gravity smashes right into the chaotic, probabilistic world of quantum mechanics. And solving the mysteries of black holes probably means solving the deepest mysteries of reality itself. And that brings us right back to the ultimate question, doesn't it? Black holes aren't really just objects. They're questions being asked by the universe itself. They force us to wonder, what even is space-time? What is information? And when the universe's two greatest ideas completely contradict each other at the edge of a black hole, what incredible new truth is waiting for us to find? If information really can't be destroyed, where on earth does it go? That's the mystery they leave us with.